This video features the mission scheduler designed for a smart swarm of Earth remote sensing satellites working together in a coordinated manner. The mission scheduler appoints satellites and ground stations and schedules their acquisition and downlinking operations using the multi-agent approach. This means that the schedule is created via interaction between software objects or agents, namely satellite, ground station, and target area agents, which negotiate and agree on all the acquisition, downlinking, and reception operations in real time. This is the Chief Designer Station, which demonstrates the operating principle and functionality of the mission scheduler. The station has 9 screens and 3 terminals. The terminals are used for station control, and the screens display the running processes and scheduling results. Let's take a closer look at each of the screens. The 3 screens to the left contain input data for the current task. The test case shown here uses a configuration of 3 satellites, 7 ground stations, and over 400 acquisition requests. The operations are scheduled for a 10-day period. The first screen shows the current configuration of satellites and ground stations, with an indication of parameters that are critical for scheduling. For example, each satellite has a memory limit, so a satellite cannot take images of all available areas and has to choose between image acquisition and downlinking. For convenience, each satellite and each ground station is marked by its own color on all the screens. The second screen is the current imaging map showing all the target areas and their locations. In our test case, there are 402 target areas, which correspond to the biggest Russian cities. The map also shows the level of priority assigned to the schedule quality assessment criteria. In our test case, fast data delivery and high image resolution. These 2 criteria can certainly contradict one another, so the system uses the convolution of criteria with specified weight coefficients. The third screen contains the event log. The mission scheduler classifies any change in the input data, such as a new acquisition request, satellite failure, or ground station outage, as an external event. All the changes are displayed on the screen in chronological order. The middle column in the screens shows the mission scheduler's internal state. The top screen depicts a physical world model, including a 3D Earth model, satellite orbits, target areas, and ground stations, and simulation of their relative motions. By selecting a satellite, you can view the short-term acquisition and downlinking schedule. The fifth screen illustrates the links established between the satellites, target areas, and ground stations in the process of schedule self-organization. All the agents are shown by circles, gradually changing color from red to green until the agent fulfills its objective functions. The request agents seek to have their request fulfilled as fast as possible and to obtain imagery of the highest resolution possible, while the satellite agents try to enhance their utilization. Once the request is included in the schedule, links are built between the request circle and the selected satellite and ground station circles. Unscheduled requests are marked in red and stand apart. The sixth screen demonstrates the satellites' schedules. There are 3 satellites in our test case, so from time to time the screen switches from one satellite schedule to another. The screen shows the satellite coverage with all the target areas and ground stations and the 10-day acquisition and downlinking schedule. The memory fill-in diagram is also provided to remind of the memory limit. The right column features the scheduling results. The 7th screen contains the agent negotiation log, showing a chronological sequence of messages exchanged by the agent in the course of scheduling. The diagrams in the 8th screen show the evolution of the schedule quality in the course of schedule self-organization. The agents create the schedule by iterations. At the initial time point, nothing is scheduled yet. No links between agents, complete chaos. But step by step, the target area agents negotiate the placements with satellite and ground station agents. First, they occupy vacant slots and then improve positions by making coordinated swaps and shifting the schedule. After the system has found a balance between agent interests, which can't be improved any further by trials, the system stops and delivers the final schedule to the user. The upper left box graphically illustrates the mission scheduler's objective function, which is a sum of objective functions of the individual agents. The upper right diagram displays the number of request agents split into 3 non-intersecting groups. Red color marks unscheduled request agents, yellow color marks the agents unsatisfied with their placements, and green color marks the agents fully satisfied with their placements. Initially, all the requests are unscheduled and marked in red. Once the scheduling is complete, green color will prevail in the diagram. The two diagrams in the bottom show a change in the number of images taken by each satellite and received by each ground station. The ninth screen displays the resultant schedule quality indicators, which include the amount of data acquired by each satellite and received by each ground station, percentages of scheduled and unscheduled imaging areas, and average values of these criteria. Now the mission scheduler has a schedule ready for the initial configuration of 3 satellites, 7 ground stations, and 402 target areas. But the scheduling process does not end here. The key advantage of the proposed approach is that the mission scheduler can adjust the schedule whenever a new event occurs. New events are input using the terminals. We start by adding a few new requests using the Create Mission terminal. To add a request, the user should simply pick a point on the map. The mission scheduler will automatically find the coordinates and the geographical name of the new target area. Let's see how the mission scheduler handles the changes. Several new lines describing the new target areas have appeared on the event log screen. For each new request, the mission scheduler has created a request agent, which has negotiated and agreed its slot in the schedule with the satellite, ground station, and scheduled request agents. As the next step, we change the space system configuration by removing several ground stations on the Create Swarm terminal. If any of the resources have been removed, some of the missions scheduled earlier will no longer be possible. The links in screen 5 will disappear. Unscheduled areas will try to find a vacant slot on the remaining resources. Finally, the schedule will be readjusted to enable the receipt of imagery by other ground stations. Now we'll try to disable Satellite 1. Its missions will be tagged as unscheduled for a while, and after negotiations with other agents, will be redirected to other resources. The user can visually track the changes on screen 8. Removal of a ground station or a satellite will result in the objective function decline. However, the mission scheduler is able to effectively deal with the changes by rescheduling the mission and rectifying or mitigating the decline without invoking the removed ground stations or satellites. The user can both reduce and augment the swarm. Let's add a new satellite. The agent's knowledge about satellites is formalized into ontology that can be edited on the relevant terminal. The satellite attributes include orbit and camera parameters. Users can specify their values before adding a new satellite. The new satellite's agent determines the orbit and tries to draw over both scheduled and unscheduled requests by offering a better deal. The more requests the satellite gets, the higher the satisfaction of its agent, which is confirmed by color change to bright green. With the mission scheduler, the user can edit satellite and ground station parameters. For example, reduce the memory size on any of the satellites. With memory storage limited by the user, the satellite will have to drop several requests that no longer fit in the memory. The schedule will be updated, and the unfulfilled requests will try to find a vacant slot on other resources. As the final step, we replace all the operating ground stations with a new one. Looking at screen 8, we discover dramatic changes happening in the system. Multiple events change the schedule over and over again, pushing down the agent's objective functions. In these circumstances, the mission scheduler vividly demonstrates its unique adaptability by quickly restoring the damaged schedule and rescheduling the satellite resources on the fly in real time.